Okay, it's noon time, so we'll get started. It's so soon, we're already on week 6, okay? And this week we will be going over to the architecture of the robot, okay? Architecture of the robot. And any questions so far? No question? Okay, anyway. Today is actually the weekend before the Thanksgiving week. Okay, so basically, I think that some student may already go for vacation, but we just have 8 week. We just have 8 week course, so we cannot cancel today's meeting. Any questions so far? Hi, Kevin, how are you?
I'm good. How are you, Professor?
Okay,
No
so
questions yet.
yeah, no problem. Yeah, so because I'm happy some students still come for today because a lot of students I think right now probably on vacation, travel around the world. Okay, so we'll go back home maybe. And today we are going to talk about the architecture of the the robot. Okay, first let's review the robotic structure. So this part we want to talk about the overall architecture. So overview, you need to know about the logical units of the robot. Okay. So you have a robot arm, you have a robot arm that we actually calculate the XYZ and theta and the D, okay, those kind of parameters, whatever, control variable and workspace. So we talk about how this arm move, how to control the theta, everything. And we also will talk about the possible reachable region that's actually workspace. Okay, so but that's not enough. That's just the manipulator. Okay, that's just the manipulator. Next one, we are going to talk about the architecture and overall how to build a whole robot. Okay, and the first thing we look at is actually this feedback loop model. Okay, this feedback model. So you have your manipulator, and your manipulator including two things. One is your working arm. So maybe the manipulator is the robot arm. The other one is your mobility, your wheel or your leg. Okay, whatever make yourself move. But these two together will change your environment. You may move something, you may actually do something. So this environment basically is what you see, the robot see. Okay, so the robot may be right here. And then he would actually look at whatever here. And then using the camera sensor, we call it sensor, and then look at it and then modify the model. So the model actually is a mathematical model that mimic the outside environment. So you see it, you build the different model parameter right here. And that's where you sense for the environment. Then you make your plan to move over here, and then your wheel, your leg actually do the movement. So you move on to there, or you change your robot arm to take something. So this is the overall structure. Okay, so let's see. So let's look at one thing. So Tesla's dashboard, okay, Tesla's dashboard. Let's see. Let's actually look at Model 3. So it always comes with the computer, right? So it also have actually the map that where your car is. Let me change the searching. Say Tesla computer screen Model 3. Okay, it will be, let me choose a better one that clear. Actually, always too small. This one maybe. Okay, this one, let me zoom it in a little bit. So basically, I think this is not enough. Actually, it will show you where you are. And usually Tesla also have a screen that actually will show the nearby car model. So that what I want to say is that you have a Tesla car and it's used primarily using camera to sense the nearby obstacles and cars and possible traffic light, all kind of things. And then those information come back to the computer to mark different new obstacle or moving object or people, okay, whatever there. So that's your environment, your mathematical model. So this architecture wise, what we are talking about right here actually is you do sensing, and you sense your environment. So your environment is kind of here. Your sensor take the capture using the camera, and then you actually build up your mathematical model to mimic your environment. And this mathematical model being shown on the dashboard. So that computer will show where your car is, where are the nearby cars and traffic lights, all kind of thing. And then if you have a self-driving, the car will steering over it to find a better path, okay, whatever. So that's all self-driving. So self-driving including the wheel and actually your accelerator, your whatever, okay, car motor control will be manipulated by it, okay. And then the sensor part can use a full camera, all kind of camera. That's a Tesla solution. You also have a Waymo that's using radio by Google, okay. So that's different sensor with give a different kind of solution. People say that Waymo one is actually better than Tesla's full camera one, but I don't know. My son have a Tesla Model 3, but it's working fine so far. Any questions so far? No. So we done this architecture primarily because that let's see. In computer science, a few subject is very crucial, very important. If you want to apply for master degree in the named university, say Stanford or Berkeley, whatever, usually they require a few important course. The important course that the master program usually need is actually programming language. And the compiler. Okay, another one is operation system. And yet another one is the algorithm. These three usually, if you are pure computer science, they will require it. If you are computer science and engineering, usually they will also require computer architecture. Okay. So this is computer architecture nowadays. I would say if you take the computer architecture course, it's so easy. They are talking about all times processor design. It's so easy. So I would say robotics is the new computer architecture. Because the day that people develop the computer architecture for microprocessor, say CISC or RISC, I think it's already becoming the traditional industry. So no longer that important because people know about it. Every third world country may be able to build a processor as well. So it's no big deal to study the computer architecture. But robotics, drone, full self-driving car, this is a new frontier. Okay, there may be more new robot will come. So the computer architecture will robotics will become the new computer architecture. Future computer format will be based on the robotics model. Okay, that's what we actually look at. So that's why I keep emphasizing that to study those kind of the control loop variables are so important. Okay, that's our main topic so far. The modeling of our robotics is so important. So first one, you still need to have an overall view of this logical unit of loops. Okay, so you know about what you are controlling. So over here, we teach you using MATLAB or Python lab, okay, to do mathematical modeling for the manipulator and the control variable. Those kind of things, we call it signal path. Okay, if you design a computer architecture, first thing you need to decide it is the data path, how your instruction get fetched from your memory, right? And then put those instructions into an instruction and then do decode, right? Instruction fetch, then decode, and then execute, and then write back to the register or memory, right? Those are the data paths. We call it data paths. In signal processing, we talk about the different stages of the signal processing. So we call it signal paths. So the so-called signal paths, including how to control the theta, how to control the D, and also how your movement to actuate your robot and get AYG, and then sensor sense your motion, and then try to compare with the existing path design. So the theta and theta, you actually tune the theta in order to get it. Okay, these are, we call it signal paths. So first thing, we teach you how to do mathematical modeling for the signal paths. Now, something more we need to design is your path-spanning unit, your controller, your actuator. Okay, these few different components, also the sensor part. These few different things that are also important in your architecture. And overall, the control, the planning part is by itself. This one is a control unit. This one is a CPU. Okay, by itself is CPU. And the old days computer architecture is only on the CPU. The other control part is considered to be EE, to be some other control unit. But the instruction-based controller that actually say Intel design or the AMD design, we call it CPU. But there are still a lot of AI computation or arithmetic computation. You need other GPU or something else to help you to do calculation. Okay, and robotics it is studying the overall structure. So we say that it's the future computer architecture. Okay, it's a future computer architecture. So first one we will talk about is a sensor. Okay, the sensor. So the sensor basically sense the physical property of the outside environment, including maybe temperature, maybe location, maybe color, maybe humidity, maybe speed, maybe chemical pH value, okay, how much acid or base they are, or displacement. Then you sense the physical property and convert it to electrical property, maybe voltage, maybe current, maybe resistance, maybe luminance level. And then you can sense it for analog processing directly, or you convert it using AD converter to convert it to digital and then do digital signal processing. So that's the first step you do from the environmental property to electronic signal. Okay, and electronic signal can be digital, can be analog. Okay, and here you talk about your signal coming in. It can be low level image, can be middle level image, can be high level image. So that depends how much you look at it. Okay, so let's assume that we do have a picture. And then those cars may be blurred. Okay, you have a car, and nearby have more cars. Those cars may be blurred. You cannot see much. So low level image means that you remove those the noise. Okay, remove the blur part, remove the background darkness, whatever those kind of things we call low level image processing. Then we have mid level image processing, means that we try to do say object recognition, and then segmentation, and then edge detection to figure out the boundary of each object. But this we call it middle level process. And those data you can continue to try to do pattern recognition to recognize, oh, this one actually it is a Toyota Prius car. So those kind of things is high level. This we no longer call it image processing, we call it computer vision. So low level noise removal, computer image processing, and then high level computer vision. Okay, these are different level of image processing. And then this what I just talked about. Okay, and then you have the pattern recognition, and then you actually will extract also extract the soundtrack as well, and those soundtrack will also provide some signal. Okay, whatever, that's also important. So they are audio, they are voice recognition, they are image, they are vision computer pattern recognition. So a lot of things and help you to build your model. So you sense, and then you need to provide those data to feedback to your CPU, the planning part. Okay, second one is the actuator. Actuator is before your manipulator. Manipulator is your robot arm or your wheels. So actuator is the one that controls it. So this actuator actually is opposite. You get your control variable, say theta, and then you need to convert it to voltage. And then voltage will actually change the controller, maybe motor, maybe some temperature controller to tune your temperature to change the speed rotor of your wheels. So something like that, and then you change the physical property. Okay, so but if you have a sensor and actuator together, that's we call it transducer. Okay, if there's a term transducer come, that actually means that two-way sensor plus actuator. Okay, whatever. So you have signal pass, and we talk about those front-end sensor and actuator. Now this one you need to build an end-to-end model. End-to-end model means that from the physical property to sensor to controller, go back to actuator and release the physical property control signal. This we call it end-to-end model. So in your cell phone, you from transmit side to the receiver side, the whole signal process, we also call it end-to-end model, end-to-end signal model. So your MATLAB or your pilot or your Python coding, you need to build the overall end-to-end model, and then converting that mathematical model into a real hardware design. Okay, hardware design. It can be a hardware design and also maybe including a software design. You need to build this end-to-end model first. Okay, and then you realize them into, say, processor, ARM processor, actuator, machine learning unit for the sensor, and planning part. Okay, whatever. Any questions so far? No? No question? Okay, so far we talked about the overall model. And this overall model is what you want to build your controller, your sensor, your CPU, and also your actuator, okay, to control your things. Now the control loop, okay, control loop can be more complicated. You will have to design a control loop based on the mathematical model. And here we have a lot of S, whatever. This is actually the model using the so-called Laplace transform, okay? So if you solve the differential equation, it's very difficult. But if you actually convert it, transform it into Laplace transform, it would be much easier. Any question about this one? So to study this in college, usually computer science major student do not study this, okay? It actually is a basic course called Signal and System in electrical engineering majors, okay? If you go to study in mechanical engineering, they also have a dynamic system course that can help you to understand this kind of system design, okay? So this is not computer science discipline course. This one is a double E course. Okay, whatever. This we don't want to go into detail here, okay? Not for computer science major. But if you really want to study robotics, some signal and processing knowledge is necessary. Otherwise, you cannot go into the control part. Okay, so each one of the electrical drive will have a transfer function. Okay, the transfer function means that you have right here, you have a K, your control variable versus the signal from the processor. Okay, that's called the that's called the control variable. That's called okay. So there's one thing called position per control. That's called trend. Let's see. You already take. Okay, this one that's called electrical drive model. From your environment variable to the control variable. Okay, they are different kind of control variable and in the loop. So there is a velocity control generator. Okay, and then this is the model for it. Okay, because a lot of Laplace transform, so I don't go into detail there. Okay. Torque control generator. This one usually is you have a rotor, and the rotor, how fast you want to control your rotor, you need to control the torque, okay? And then this one is to the mathematical model for it, okay? Okay, whatever. Is including too much mechanical engineering terms, okay? For gears, how the variable rotation versus the wheel ratio, okay, whatever, to control it. So that's actually build up a mathematical model for the pendulum actuated mechanical gear, okay? And then position control. Position control and velocity control is based on your position, your XYZ, that's your position. Okay. And also your velocity. So velocity and the position and the displacement. Displacement is the integral of your velocity. So here, this one may be velocity, this one is integrator, okay? And you provide the control back to your loop. So this loop actually have both velocity and also the position control, okay? So basically what I want to say is that you build your loop, feedback loop, and then convert it to a differential equation, and then those differential equations being transformed to Laplace transform, and you get this model. And then joint space control. Okay. So here, let's look at this joint space control. So you have a robot arm. Your control maybe in the old day, you can use every control function can be used the RLC control. RLC is a resistance, inductance, and capacitor. You can build with that. But that's old days electronic design. Okay, nowadays it's become all digital. So RLC and controller can all be replaced by digital discrete equations to model it. So you actually put the impedance law and kinematic dynamic and also torque control. You calculate here and then you control your loop system, okay, to control your robot. And there are tons of different kind of mess over there. Okay, anyway. And then you can have different loop control equation. Okay. So this whole lecture 10 is basically give you the overall structure of the sensor and actuator. Okay. Then lecture 11 go to different things. You will go to image servo and servoing. Okay, so basically lecture 11 go to talk about the sensor part. Okay, if you use the camera, okay, then you need to know about your image vision and the servoing. Servoing is for the actuator for control. Okay, so you need to know about robot vision. Here we do have a project on OpenCV, open source computer vision, also in the Python domain. Okay, you can install that to try the computer vision. Okay, so computer vision, first you need to know about what is computer vision, and then knowing about how it is used in robot environment. Okay, so the purpose of the machine vision is to analyze image and produce description of what they are imaged, and then how to update your mathematical model. Okay, these are the purpose. So you need to do image transformation analysis and understanding the low level, middle level, and high level imaging. And then you have sensor. Sensor is the camera. Okay, if you do vision. Here, I need to emphasize sensor may not be a camera. It can be a radio. It can be something, and you need to build your environmental image. Okay. So you may, if you use camera, there is a camera projection model from your SYG to 2-dimension UV. Okay, that's actually is an imaging model that you will build. Okay. So here tell you what is the scaling question about the image. And image, when you build, there are distortion, okay? And you kind of need to build up your model to handle it. And there are angles, and then you need to reconstruct it. Okay, here a lot of details. I just tell you what the purpose of this different calculation. You need to understand them. Okay, if you do computer vision. Okay. Okay, whatever. So sometimes you don't do full color computer vision. You do vision scanner using laser scanning. So for example, you actually may have a fisheye sensor that's omnidirectional. So you want to have a panorama view. You use a fisheye camera. It's not really taking a square image. It actually is like fisheye camera. So you can look at it as this, and then using computer to actually recover it. So this panorama means that there's a room, and you may have a banner panorama hanging over, but it's just surrounding the house. And this fishbowl eye can actually take such image and then being used to recover the whole 360-degree view of the room. Okay. So there are something like that. And there are sensors that can sense in low light condition and recover the object. Okay. So for this sensor part, there are measurement frequency, measurement uncertainty, and camera position problem, and sensor dimension. You need to use a lot of math to recover them. Okay. Visual servoing. Visual servoing is that you use your video, okay, the camera you take to provide the servoing control. Okay, that's called visual servoing. So that loop, you can using the logic model of having the feature extraction. This feature extraction is like object detection, edge detection, and those middle to high level vision detection. And then based on those object detection value, you determine the SYG in the model as a post determination, and then feedback to your control loop. Okay. Okay, and the control loop can be PID control loop. Okay, it's integral, maybe base, maybe differential base, maybe proportional control, whatever. This PID mean P is proportional, I is integral, D is differential. Okay. So you may have a visual that you would look like to look at whether your robot arm can pick up something or not. Okay. So that's called visual servoing to manipulate maintaining related relative object position. Okay, so your camera can be fixed, outside fixed, can be on your robot head. Okay, so each way your camera will see different things, and your mathematical model recovery algorithm must be different. So far, any questions so far? Any questions so far? No? So we are talking about so far is to build a model for a sensor, okay? Then the servo-in structure, it can be two types. It can be point-based and versus image-based. Image-based, we know image-based is that you take picture and then recover by the model. Okay. Point-based is different. The control is different, and point-based and image-based can actually using the different camera head. Okay, so one is fixed one is actually using the. So if you are this one position based, you will do feature insertion and then determine your pose. Okay, recover it. That's actually point based. If you don't recover, you just calculate XYZ that actually is your image based. Let me see. Okay, no question. Okay. The next one is a position based. So position based, you do feature insertion, you got a feature. So the feature maybe is a age, and then you use those age to say you have a car age, and you determine where the car is. So this kind of thing we call it point based. Okay, it's not just taking the picture and then analyze picture. Okay, that picture inspection type of camera, we call it image based. Okay, and we know that Tesla is purely on image based. Okay, whatever. And this one is image based servo. Okay, so there are some pushing and passing about each one. Okay, and you choose. Okay. So they are open loop control. They are end loop and closed loop control. Open loop means that you just look at the here, okay, and you use your robot arm to reach it, but there's no feedback. Okay, there's no feedback. You just keep approaching it, no feedback. With the feedback, we call it closed loop. You know, you feedback and you need to actually keep moving toward the target based on feedback. And servo-in is that you minimize the difference between your expected location and your location of observation. Okay, and trying to minimize the difference. Okay, trying to divide. So okay, whatever. These are your controller. And your coupled image robot Jacobian need to include in your image plane, your Cartesian plane, and your join spaces. These three things you actually use a two Jacobian to do conversion from your image to the transformed image in your model that's called Cartesian space. And those XYZ Cartesian space need to convert it back to your control variable. So here, this one is control variable. This one is XYZ. This one is the UV that you observe in the environment. Okay. The image that you take. Okay, whatever. And then you use mesh to recover it. Okay. And this one is a more detailed, more logical position-based visual servoing. Okay, some more mesh. Okay, and talking about how things taking picture and model. Right here, I think you can see that it used the edge detection, okay, for the object to identify the object. And then a lot of things that you need to calculate, okay. Image base, you need to look at the image value, okay, and there's an image Jacobian. This is not between controller variable and the XYZ Cartesian space. This is not. This is between your UV that you observe converting to the XYZ. Okay. Okay, whatever. And then the picture that you take need to be converted to your internal model. Okay. So this is just show you how it can be done. Okay. Okay. And the application, you can use it for microsurgery. Okay. Microsurgery. And then you can use it for computer-aided design, okay, for the vision. And then we talk about OpenCV, okay, computer vision, open computer vision. So here, just tell you how to get the model, get the package, okay. And then we demonstrated how to do electronic shuttling using your computer to take picture. Okay, and then what is exposure time? What is the gamma correction? And what is dynamic range? Okay. So here is simple look and color space. Color space, usually you have RGB color space and the CMYK color space. RGB usually is used for monitor. CMYK is for printer, okay? And then you can have the color wheel, okay? And this HSV model as well. There are several models, several color space. Okay, and this one tell you what is the RGB, okay? And RGB can come from several different kind of camera, okay? And then you need to convert it back to XYZ. okay, and then using different tools as well. So here talk about Python code iteration of single image. Okay. So talk about what is the pixel in the OpenCV frame and gray color conversion from RGB to YCBCR. Okay. YCBCR usually is used in the TV, okay, in TV. Okay, then there's a mathematical model. And what is low image function in OpenCV? So I do have this image loading program to take a picture on Macy's, the soccer players, okay? And then image transformation. The image transformation mean also related, have the translation, resizing, and rotation. Okay, and we do teach you how to do translation. Is that your image move to different location. We actually use the OpenCV to it, and then you can also do resizing. This is scaling, okay, scaling. Make the image bigger or smaller. And then rotation, to do image rotation to get a different angle. And then deal with color space. Okay, deal with color space, I'm sorry. We use the conversion from RGB to the gray level, okay? And frequency domain. Frequency domain can be used to detect the edge, detect the object. So because we need to do frequency domain change, so we do have high pass filter and low pass filter. Okay. So this different filter actually will do effect on the image. And usually high pass filter will detect the edge. Low pass filter will remove the noises. Okay. Okay, and then there are different image processing masks. And they also do edge detection. Okay, all kind of edge detection algorithms. So this one is edge detection from the picture to detect the edge, okay? And you can actually convert it to black and white, and then the edge will be more obvious. And then you can also do contour detection. Contour detection means that I only care about the boundary. So this object, if you do contour extraction, you'll be the green contour. And then here, this robot arm is what I built. And then I take a picture, make it convert it to black and white. Okay. And it's like this. This is gray level. And from the black and white, I do detection for the boundary, for the edge detection. So that would be the blue one. Blue is edge. And further, if you want to do computer imaging, the feature computer vision from the edge, you can verify what kind of robot it is. Okay. Okay. So here we quickly go through different image processing and computer vision. And key point is that we're not trying to teach you in such a short time. We actually still go back to the prime main purpose is to go over the basic topic of how you can restore your image and doing feature extraction and trying to provide this high-level image processing result to computer vision algorithm to do pattern recognition. Okay. Any questions so far? Any questions so far? No? Okay, so machine learning and AI, okay. Machine learning and AI, it's a primarily application are computer vision, finance, and bio health science. Okay, the three major domains. And robotics is the champion in this computer vision. Okay, so you need to actually learn to extract those low-level image informations, and then those low-level information will be converted to edge detection or higher-level feature extraction. So edge by itself is the feature that robot. So here you from your camera, you have JPEG, and then you extract those edges, and those edges are used for pattern recognition. Okay, usually. Okay, so computer vision is very important. It's a separate class, but right here we just tell you how computer vision can be used in computer robotics. Okay. Any question? No? If no question, today we are up to here, okay? See you next time, but wish you happy in Thanksgiving week, okay? See you, bye-bye.